Hi everyone, this is video 21, and today is an exciting day because this is the last content-based video that I'll be making for this first part of this course, Introduction to Programming Paradigms. Now, this last topic that we're going to be talking about is also one of the most important topics in computer science. I know I say that a lot about a lot of things, but this is really, really important, and you'll see in some of the applications of this idea. But today we're going to be talking about a very important data structure called trees. Okay, so we've actually seen a little bit about trees. We've seen it used for expression trees and tree recursion. But what you probably didn't know is that the tree is one of the most important data structures in computer science. So what is a tree? Well, a tree, it consists of a root and a series of branches. And these branches also happen to be trees. So as you can see, the trees have a very natural recursive definition because the branches of trees are also trees. Now, there's some terminology associated with trees. For one, there's a leaf. So a leaf is shown right here. Basically, a leaf is a tree with no branches. They're basically the end of a tree, or a branch of a tree. Then there's also these nodes. We refer to nodes as the entries/values of the subtrees. So like here, right here, we have a subtree. The node of that is 2. And these, so this encapsulation right here is something that represents a branch of a tree. Here's another branch right there. Okay. So, obviously we want to have an idea of a tree, and the first question you should ask yourself is, how can I make a class for a tree? And when you think about that, you should think about how our constructors should work. Well, in linked lists, we needed a first and a rest. So, but in trees, our two main ideas is we have an entry value, and we have the branches. But the problem here is, there could be any number of branches. There could be a tree with 2 branches. It could be a tree with 5,000 branches. How do we basically handle that? So I want you to think about this question for a little, and I'm going to spoil the answer in 3, 2, 1. What we can basically do is we can represent the branch as a sequence, and one of the easiest sequences to work with is the list. So we can represent branches as a list. So now, using this idea, we're going to build our first tree. Tree data structure. Okay, so tree is going to be a class, and so now using our idea within our constructor is going to take an entry. So this is the entry of a particular node in a tree, and then we're also going to have some reference of branches. And so, like a linked list data structure, we want to have a notion of a tree with no branches, which is a leaf. So if we don't pass in any branches, we want it to automatically be empty. So we can do that by a default argument of the empty list. Now, what we have to do is we have to basically make sure that first we bind the entry to an instance attribute. So I'm going to say self.entry is equal to entry. And then, like in the linked list, we have to make sure that we get a valid tree, right? So a great way to do that is an assert statement. And so what's a valid tree? Well, a tree, by definition, is a list, is an entry or a root value with a list of branches that's also trees. So we have to basically go through every branch in our branches and check that it's a tree. So what does it mean to be a tree? Well, we basically assert that the branch is an instance of the tree class. So this is very similar to our linked list definition. So what you're going to see is trees and linked lists are somewhat similar because they're recursive data structures. And then after we check this, we can then bind an instance attribute of branches to whatever branches we passed in. Okay, and then with trees, it's also going to be useful to have some way to represent them, and the way we represent them is basically going to be the same as our linked list. So this will help when we do testing and stuff. So remember, in our linked list, we wanted to have, so I'm going to basically copy, it's going to really be a copy of the linked list representation, where we have a tree that takes in with parentheses and has a notion of an entry and a branches. So we're going to fill in that entry and branches with whatever the format of the self.entry is, and what we're going to call the branches string, similar to how we had the rest string in the linked list. So I'm going to initially have my branches. So basically, one case I have to think about is, what if there's no branches? So if there's no branches, so note also, one thing I want to note is that notice I'm having self.branches stand alone. So what this means is that self.branches, if it's empty, turns out that an empty list is by default has a false value. So if this is not false, this is going to be true. So this basically says if there's no branches, I'm going to execute this, and what I'm going to do is if there's no branches, then I have nothing to put in my string. So I make it an empty string. And then otherwise, my branches string is going to be just like the linked list, a comma. So it's going to have a series of commas with the way we represent the branches, the rest of the branches. So once we do this, this is our definition of the repr string for the tree class. So let's see how this works. So I'm going to make a very simple tree. So this is just going to be a leaf. So we see that we represent it as such. So what's the entry of this leaf? 1. And what should be the branches? It should be an empty list of branches because there's no branches for this tree. So let's see that. So it's an empty list. Now, let's make our tree a little more complicated. Tree of 1, and then now we want it to have 2 branches. Okay, so what does it mean to have 2 branches? Well, you have a list of length 2, and one branch is going to be just a leaf 2, and the other branch is going to be a leaf 3. So this is how we represent trees. And I'll show you more of a visualization of how this works. But basically, so this is our tree, and our entry value of the tree, this is the root value, is going to be 1. And then we can also get the branches. So there are 2 branches in this case. So you see that there's a branch that consists of a leaf 2 and a branch that consists of a leaf 3. So let's look at an example of how we can basically visualize this. So again, here's our class for tree. And so what we just built is, in this example, was the following tree. So we have an observation that we have a root entry of 1, and there are 2 branches that are leaves. So the way we represent that is the following. We have a tree of the root value 1, and then 2 branches, and these branches are basically stored in a list, because there could be any number of branches. There could have been 5 branches, and then there would have been 5 elements in the list. And so we see that there's an entry, and then the branches are the following. So this is a simple example of how to construct a tree. So now let's look at a little more complex example. So what we want to do is define the constructor for the following tree. So take a moment to see if you can figure out how to exactly define this constructor, and you really use the recursive definition of a tree in your solution to this. So the way I'm actually going to show you the solution to this is I'm going to do a little bit different method here. So I actually discovered today this option that you can have a pen on a PowerPoint. So that's pretty nice. So what I'm going to do is I'm going to actually write out this definition of the constructor. And I'm going to basically go through my thought process. Well, what I first notice is that we have a root value of 1. So that's the first thing I'm going to keep in mind. Okay? So I'm going to basically have my tree. My tree is going to have a root value of 1. So that's the first thing I'm going to keep in mind. Now, what other branches? Well, this has 3 branches. So we have 1 branch here, and that's the first one I'm going to worry about. So how do I represent this branch? Well, this branch has a root value. So remember, branches are always a part of a list, so we make a list. And then this has a root value of 2. Okay, so how do I represent that? Well, it's going to be a tree. Because remember, each branch is going to be a tree. And this is going to have a root value of 2. And then now notice that this branch also has 2 branches in it. So this subtree has 2 branches. And what are the 2 branches of the subtree? Well, so basically we have another list, and one branch of that is just a leaf that represents 3, and another leaf that has the value 4. Okay, so now the tricky part is we have to figure out how to close this off. So this is the branches for this subtree right here, and then we have to close the parentheses on that. So this one, so let me just underline where these correspond. And then now, so this entire thing right here is just one branch of the outside tree, the larger tree. So now I have 2 more branches to go. So how do I denote that I have another branch? Well, it's a comma in a list, right? Because this now gives another element of the list. So now we have another branch, and what's this branch? Well, so we finished this branch so far, and so now we need to worry about this branch. Well, this branch is pretty easy because it's a leaf. So we just put tree of 5. And then we have one more branch, which is this. So we finished this one, and that is just tree of 6. And so once we have that, we basically have all the branches, and then we finished our tree definition. So this is how we represent the constructor for the following tree. So it's a very logical process. I start with the root. So I started with the root, and then I ask, hey, what's my first branch? Oh, hey, that's a tree as well. So how do I represent that tree? So slowly split it up into smaller and smaller problems until you get to the easiest case, which is a leaf. So then I have a tree of 2, and then I have 2 branches of that, and they happen to be leaves. So that's pretty simple. And then I move on to the rest, which is again just leaves. So that's how I basically, so you can do this for any size tree. Obviously some of the constructor definitions can get very long if they're very large trees, but if you really split up into smaller and smaller problems, you can figure out any of these. Okay, so now let's see how this works with an actual definition in the computer. So let me get rid of this pen real quick. Okay, so here I defined the following tree that I just drew out right there. So let's make so I had this, and that's basically copied here. All right, and so we first check the entry. It's 1, and then the branch of that. Hey, we have 3 branches. 1 here, 1 here, and 1 here, and 1 here. Okay, so and then we can actually get the first branch because the first branch is just the first element of the list. So we get the 0th index, and the first branch corresponds to this. So that's exactly what we want. And the entry of the first branch is 2. And the branches of that, well, there are 2 branches, tree of 3 and tree of 4. So that's basically how we know that this tree is the right structure. And we can do the same for the second branch and third branch, but I'm fairly confident that this is right. So whenever you want to test whether you have the right constructor, this is a good way to do it.